Hello students, this video is going to be the first of a series of lectures on the class 11 physics course belonging to the CBSE curriculum. The first video is not actually on per se the physics syllabus. It is going to be the basic math that is required for the physics course. So some of the mathematical concepts may be familiar to you based on your high school experience, but some of these concepts are not familiar to you, and you would need those concepts in physics during the next 2 years of your study. So a series of topics are going to be covered in this video, and each one of these topics is very important from the point of view of a physics study. Right, let me start with the first concept of exponents. What are exponents and how one can manipulate these exponents, because we'll often encounter exponents in a variety of contexts in physics. What is an exponent? For example, I write a number, let us say 4. Explicitly, this number does not have any power on top of it, but it always means that this is 4 power 1, 4 raised to the power 1, and you know the result is 4. Suppose I write a number 5 and say I raise it to the power 3. What does this mean? This means the number 5 is multiplied onto itself 3 times and result is 125. Now this is an exponent number. It has two parts. This part 5 is the base number and this part 3 is its exponent. So the number as a whole is an exponential number. Now we can clearly see from this example that the base number as well as the exponent in this case both are positive numbers. But there is no restriction as such that this should both be positive numbers. Any real number including fractional numbers are allowed as well as both positive and negative numbers. So suppose if I write the same 5 raised to the power minus 2. Here the base number is 5 in this case and the exponent is minus 2. What does it mean? This just means that this is 1 over 5 raised to power 2. This is nothing but 1 over 25. This is the meaning of a negative exponent. Right. What about fractional exponents? I write, let us say, 25 raised to power 1 by 2. In this case, the base number is 25 and the exponent is 1 over 2. And this has a special name. This 1 over 2 exponent has a special name. It is called the square root. So it is square root of 25 and the result in this case would be 5. In the same way, if you write 125 raised to the power 1 by 3, this also has an exponent of 1 by 3 for the base number 125 and this also has a special name. It is called the cube root. So this is nothing but cube root of 125 and this the result would be 5 now, because 5 when multiplied onto itself 3 times would result in 125. That is the meaning of cube root. Now therefore, to generalize all that we have covered so far, we can always say the exponent number will have a form x raised to the power y, where x is the base number. X can be positive, negative, both integers and fractions. So x can be any real number and the exponent y can also be similarly any real number. Now there are special rules that one has to also understand going into exponents. Now we'll cover some of the special rules for these exponents. There are some special rules when we deal with exponent numbers. For example, any base number x raised to the power 0 will always result in 1. The result is always going to be 1 if any base number raised to an exponent 0. Any base number raised to an exponent of infinity will result in infinity. Of course, here the sign for the infinity is a positive sign, that is positive infinite number. Similarly, any base number raised to the power minus infinity will lead to 0, because this is nothing but 1 over x power infinity. X power infinity is a huge number, so that is also equal to infinity, so it is 1 over infinity, therefore this should lead to 0. These are some of the rules that one has to understand while dealing with exponents. Now additionally, there are some specific rules that we will cover now. First, what is called the product rule of exponents. What is this product rule? Suppose I have a base number x raised to an exponent m, and the same base number x is raised to another exponent n. Now the resultant would be x raised to the sum of the two exponents m plus n. This is called the product rule. There is something called a quotient rule in exponents. What is this quotient rule? Quotient rule is nothing but a base number x raised to the power n m over the same base number x raised to the power n is nothing but the base number x raised. Right. The next rule is the first power rule of exponents. What is the first power rule? That is, when you have a base number x raised to the power m and the whole thing is raised to the power n, then the result would be x raised to the power of product of m and n. This is the first power rule. Now apart from this, there are some other power rules which can be called as, let's say, other power rules. What are these other power rules? For example, I have a product base number x multiplied by y raised to a common exponent m, then the result would be x raised to the power m multiplied by y raised to the power m. In the same way, I have a fraction x over y raised to the common exponent m. The result would be x raised to the exponent m over y raised to the exponent m. So these are some of the common rules in exponents that one should know before manipulating the exponents wherever one encounters these objects in physics. In physics, often we would encounter numbers that are too large or too small. In such situations, we should use what is called scientific notation. Right. For example, when we express large numbers, we would normally try to express it as a product of two numbers. The number of significant digits multiplied by 10 raised to some power. For example, I have a number, let's say 23,500. This is not a very scientific way of representing a number. The scientific way of representing this number would be 2.35, because we are taking three most significant digits here. So the significant digits are 3 here, multiplied by 10 raised to the power 4. Right. The same number, let us say, with some modification, you have 23,560, let us say. Now the number of significant digits have increased from 3 to 4 here. Therefore, when we try to write this number, we can write 2.356 again multiplied by 10 raised to the power 4. So this is how one has to represent numbers in a scientific notation. Right. Suppose we have a number that is, let's say, 0.00235. Now, there are 5 digits after the decimal point, but the significant digits are again 3 digits, so we have to retain those digits. So this number can be written as 2.35 multiplied by 1, 2, 3, 10 raised to minus 3. Similarly, another example we can discuss. Let's say I have a number that is 0.02134. Now this also we have to write in terms of 10 raised to negative powers. So we can write it as 2.134. We are retaining all the significant digits and multiplying by 10 raised to power minus 2. So this is how we can do the powers of 10 for any given number, either positive or negative powers, by appropriately altering the digits and the decimal point and expressing it in powers of 10. This is a scientific way of denoting the numbers. Now again the question will come, what is 10 power 0? Anything raised to power 0 is 1, so 10 raised to power 0 is 1. Right. Now this is not a very significant information, but what is very important is there are some special powers of 10 which we should remember while doing physics. What are those special powers of 10 that we should remember? Right. Let us start from again 10 power 0. 10 power 0 is 1. 10 power minus 1 is called deci. 10 power plus 1 is called deca. 10 power minus 2 has a special name. This is centi. 10 power plus 2 is hecto. 10 power minus 3 is the very familiar milli. Whereas 10 power 3 is kilo. 10 power minus 6 is micro. 10 power plus 6 is mega. 10 power minus 9 is nano. 10 power plus 9 is giga. 10 power minus 12 is called pico. And 10 power 12 is called tera. 10 power minus 15 is femto. And 10 power 15 is peta. And so on and so forth. So large numbers are generally expressed as 10 raised to the positive exponents, and very small numbers are expressed with 10 raised to the negative powers. So it is important to remember some of these special names, because when there is, let us say, 3650 gram mass of a particular object, let us say, this should be suitably expressed as 3.65 kilogram. Here we are using this information that 10 raised to the power minus 10 raised to the power 3 is kilo. So actually this is 3.65 raised to 10 multiplied by 10 raised to the power 3 grams. So we are expressing this as kilogram. So in the same way, for all quantities such as length, mass, or even time, we can use any of these special powers of 10 to express the quantity in a concise manner. The next topic is some basic algebra that you are probably already familiar with from your high school studies, but nevertheless it is worth recollecting those. Now, algebraic equations are something that we will very commonly encounter in physics, and there are many times where you are required to solve an equation to arrive at a particular physical quantity. For example, a simple equation such as x plus 3 is equal to 0 would straight away yield a solution x must be equal to minus 3. But not all equations are going to be very simple as this. For example, one of the very common equations that you might encounter is, for example, in your mechanics course in physics is S is equal to, for example, ut plus half at squared. This is a typical algebraic equation where S would represent the distance a particle has moved in a time t with an acceleration a and initial velocity u. Now this is a very typical example of an algebraic equation which requires to be solved. One can solve this equation either for t or even for a. For example, let me try to first solve this for a. If this equation has to be solved for a, then I would write S minus ut is half at squared, and 2 times S minus ut by t squared is a. So this is how one can manipulate an algebraic equation and try to kind of arrive at the solution, right? But not all algebraic equations are so simple and easy to manipulate. For example, if you want to solve the same equation for t, you're not going to easily arrive at a solution, because you'll have this equation linearly written as, for example, half at squared plus ut minus s is equal to 0, right? Half at squared plus ut minus s is equal to 0, and you can write this by multiplying overall throughout by 2, resulting in at squared plus 2ut minus 2s is equal to 0. Now, the solution of such an equation is not so simple. You have to use what is called the quadratic formula, because this equation is a quadratic equation. In t. So this is a quadratic equation in t. So if you want to solve this equation for t, and you have to arrive at an expression for t, then you have to use what is called the quadratic formula. What is the quadratic formula? Now this equation has general form ax squared plus bx plus c is equal to 0, where our a is corresponding to this a, and b corresponds to 2u, and your c is minus 2s. In such a situation, for this equation, general quadratic equation, the solution is given by the quadratic formula. That is, this equation is an equation in x, so your solution is x is equal to minus b plus or minus square root of b squared minus 4ac by 2a. This is the solution for an equation of this form. The same way, applying this formula, one can arrive at a solution for this equation. So I have written here the same equation, half at squared plus ut minus s is equal to 0, as at squared plus 2ut minus 2s is equal to 0, bringing it to the form ax squared plus bx plus c is equal to 0. We know that for such an equation, we want to arrive at a solution for x, that is the roots of the equation. So these are the two roots for the equation, quadratic equation. X is equal to minus b plus square root of b squared minus 4ac by 2a, and x is equal to minus b minus square root of b squared minus 4ac by 2a, or the two roots of this quadratic equation. So we want to find out the solution in terms of t, that is the root in terms of t. So root for t. So a in the corresponding equation is therefore equal to a, b corresponds to 2u, and c corresponds to minus 2s. So we have to apply this quadratic formula to arrive at the solution. Right? Therefore, applying this here, I can write minus 2u plus or minus square root of 4u squared minus 4 into a into minus 2s divided by 2 times a. This is the solution for t. These are the roots for t. Two roots we'll have now. Therefore, this is equal to minus 2u plus or minus square root of 4u squared plus 8as over 2a, which can be simplified as minus u plus or minus square root of u squared plus 2as by a. These are the roots for that equation. So we have solved that equation for t. So this is one of the equations of motion, and we have solved it for t. This is how algebra comes in very handy to solve some equations in physics that you would encounter. The next topic is direct, inverse and inverse squared relationships. These are some of the relationships that we would very often encounter in studying physics. First, let us deal with the direct relationships. What is a direct relationship? A direct relationship is one in which a physical quantity, let's say y, on the left hand side is directly proportional to another physical quantity, let's say x, on the right hand side. Therefore, they are related by a proportionality constant, let's say k. So, to write it as an equation, this proportionality relationship into an equation, we write y is equal to kx. So, this is a direct relationship. That means there is a linear dependence of y on x. So, y is a function of x, and therefore y is nothing but equal to kx. So, this is a direct relationship. When we try to plot such a relationship, we'll get a straight line, a linear relationship, for example, in this case. So, y is equal to kx when you plot x along the, of course, x-axis and y along the y-axis. Now, this is a direct relationship, and the slope of this straight line is k, and the slope k is given by the expression y2 minus y1 over x2 minus x1. Right, so this is a direct relationship. In physics, for example, often you would encounter a lot of quantities that have a direct relationship. For example, when you connect a spring to a mass and the spring is attached to a fixed, one end of the spring is fixed and a mass is connected to the other end of the spring, and if this mass is moved towards the right, by pulling the mass, the spring is going to extend. Now, the force on this spring is the pulling force, and this force is equal to some constant k, which is called the spring constant, times the distance to which the spring is extending. So, this is a very well-known expression in physics, that is a direct relationship, a very good example of direct relationship. Now, this is the pulling force, therefore this Fp is equal to Kx. Now, the spring responds by restoring to its original position once the force on the mass is released. Now, that force can be called as the restoring force Fr, and this is going to act in the direction opposite to the original applied force, therefore that would be minus Kx. Even this is a direct relationship. Now, these two forces, Fp and Fr, are equivalent and they are opposite. Equal and opposite forces. Now, both these are examples of direct relationship in physics. Many such direct relationships are possible. As you study physics, you would understand that a lot of such expressions will be seen. Next, we'll discuss what is inverse relationship. A quantity y, let us say, is proportional to inverse of another quantity x, then we say y is proportional to 1 over x. Now, this is an example of an inverse relationship. Now, this is also connected and the equation can be expressed with a constant k. So, y is equal to k over x is the expression for an inverse relationship. Therefore, if you plot a curve here between x and y on the y-axis and x on the x-axis, you would get something like this. This is the y is equal to k by x curve, or xy is equal to k curve, which is a hyperbola. Now, if you want any example for this in physics, a very common example can be that of an ideal gas. An ideal gas kept at a constant temperature as you increase the pressure, the volume decreases. So, the pressure and volume are connected by an inverse relationship. Pressure is directly proportional to reciprocal of the volume. Therefore, pressure is equal to, one can write, or pressure times volume is equal to a constant. So, if you plot this function in physics, you would get a curve similar to this. So, this is an example of an inverse relationship in physics. The next topic is inverse square relationships. In physics, one of the very common and fundamental relationships fall under this category. For example, Newton's law of gravitation. Is an inverse square relationship, wherein the force of attraction between two objects having mass m1 and m2 is directly proportional to the product of the masses of the two objects, and it is also inversely proportional to the square of the distance connecting between the two objects. Now, the equation corresponding to this involves a constant called universal gravitational constant G. Therefore, the expression for Newton's law of gravitation is force is equal to G times product of m1 and m2 over r squared. So this is a very good example. This force is attractive force or gravitational attractive force, and therefore this expression is an example of an inverse square expression in physics. Another very common example that one can give is what is called Coulomb's law in electrostatics. This is another example of an inverse square relationship. So here the electric force or the electrostatic force between two charged objects having charges q1 and q2 is K, which is a constant, Coulomb's constant, multiplied by the product of q1 and q2 over the distance separating the two charges r. So here this is two masses m1 and m2. Here these are two charges q1 and q2, again separated by distance r. Now both these fundamental force laws in physics, they fall under this category of inverse square relationships. So if you plot the force along the y-axis as a function of the distance r, you would get a curve that looks something like this. So this kind of a curve will be very commonly encountered in physics. It's 1 by r squared curve. Thus, some of the very fundamental laws in physics fall under this category of inverse square relationship, where the quantity on the left side is force and the quantity on the right side is the distance, and therefore force is proportional to 1 over r squared. Therefore, to generalize this, a quantity on the left side y is proportional to 1 over x squared. Such relationships, wherever you encounter, they all fall under the category of inverse square relationships in physics. Next, we're going to discuss about logarithmic and exponential functions. First, let's deal with logarithmic functions. Logarithmic functions basically are of two types commonly. One is log to the base 10, and the other one is log to the base e. Of course, symbol for this is natural logarithm, so we use ln. So this is called natural logarithm. Whereas this is common logarithm. First, let's deal with common logarithm. Logarithm of a number in common logarithm, that is base 10, is defined as the power to which 10 must be raised to arrive at the number. That is 10 power log y is equal to y. This is how one can define logarithm of a number. So logarithm of a number is defined as the power to which 10 must be raised to arrive at that number y. In the same way, for natural logarithm is defined as log to the base e, of course, its symbol is ln, is defined as the power to which a constant e must be raised to arrive at the number, where e is the constant given by 2.718. Right. So, some very common things are logarithm of 0 is not defined, so it is undefined, and logarithm of any negative number is undefined, logarithm of 10 is 1, and logarithm of any number in the range of 0 to 1 will be negative. That is, here n is between 0 and 1. In that case, you get a negative value. Similarly, log 1 is equal to 0, and this is true for even natural logarithm. That is, log to the base e of 1 also is equal to 0. Now, there is also a way to convert from one logarithm base to the other base. That is, natural logarithm of x is nothing but 2.303, a factor of 2.303 is involved, multiplied by log to the base 10 of x. So here it is log to the base e, here this is log to the base 10. Now this factor 2.303 comes from natural logarithm of 10, which is equal to nothing but 2.303. So one can easily prove this relationship from here. Right. This apart, there is always, one has to remember certain things easily. One can, wherever required, one can apply those things. That is, log of 1 is equal to 0, as I already mentioned. Log of 10, when I don't mention clearly the base, it means it's base 10. So this is 1. Log of 100 is 2. Log of 1000 is 3, and so on and so forth. Any number between 10 and 100 will therefore have log 1 point something. Any number between 100 and 1000 will have 2 point something. That is how log scale is used. Also, we have defined here that the power to which 10 must be raised to arrive at the number y is the logarithm of that number. So we can also write this as y is equal to 10 power x, where y is called as the antilog of x. So logarithm, and the reverse is antilogarithm. We shall discuss some more rules of logarithm. For example, logarithm of product of two numbers, let's say a and b, is equal to individual logarithm of a plus individual logarithm of b. Similarly, logarithm of a fraction a over b is equal to log of a minus log of b, and logarithm of an exponential number a raised to the power b is equal to b times logarithm of a, and also log to the base e of e is equal to 1. Our next topic is areas and volumes. The students should recollect some of the information that they have already studied during their high school mensuration classes. That is, areas and volumes of some of the very common shapes. For two-dimensional shapes such as circle, triangle, square, and rectangle, you should know the area and perimeter calculations. Similarly, for three-dimensional shapes such as the sphere, parallelepiped, cube, cone, one should know the surface area formulae as well as the volumes. If one is adept at calculating these things for a given shape, then one can, wherever it is required, easily go to the application and apply these as required. So, for example, a circle is a two-dimensional figure, and area of the circle of radius r is pi r squared. And the perimeter is nothing but the circumference of the circle, which is 2 pi r, if r is the radius of the circle. Similarly, for a triangle of side A, the perimeter is 3 times A, if it's an equilateral triangle, and the area is half into base into height. For a square, the area is of side A, area is A squared, and the perimeter is 4 times A. For a rectangle of length L and breadth B, the area is length into breadth, and for the rectangle, it is 2 times length plus breadth, that is the perimeter. So we have to remember these common formulae. For sphere, the surface area is 4 pi r squared if the radius is r, and the volume is of course 4 by 3 pi r cube. For a parallelepiped, the surface area is, the parallelepiped, remember, has a shape with let's say sides A, B and C. The longer side I am taking as C, A, B and C. So you have two sides having area, so you have 2 times AB plus 2 times BC plus 2 times CA. So these are the areas that are involved. So the surface area is going to be a sum of all the three. And of course the volume is A into B into C for the parallelepiped. For a cube, the volume is A cubed. And the surface area is, there are 6 faces, each having area A squared. So it's 6A squared. Of course the cube side or edge length is called A. For a cone, the volume is 1/3 of pi r squared h if the height of the cone is h and the base radius is r. Whereas for the cone, the surface area is pi r squared plus pi r into square root of r squared plus h squared. And for a cylinder, the surface area is 2 pi r h plus r, and the volume is pi r squared h. So these are some of the formulae that you should remember. So this is the surface area, this is the volume for the cone, this is the surface area, and this is the volume for the cube. This is the volume and this is the surface area for the parallelepiped, and this is the surface area and this is the volume for the sphere. Similarly, here we have perimeters written at the bottom and areas of these figures written on the top. So it's useful to remember these formulae of different geometric shapes, and they'll come handy while solving problems in physics. Our next topic is plane geometry. So it is useful to remember some of the basics of geometry that we have learned in high school. For example, two straight lines, intersecting straight lines, will have their interior angles equal. That is, if this is theta and this is phi, then theta is equal to phi. So this is useful to remember this. Similarly, if there are two parallel lines and they are intersected by a diagonal line, then of course these two angles are equal, theta 1 and theta 2. Theta 1 is equal to theta 2. Also, because of this rule, this angle, let's call this phi, phi is equal to theta 2 as well. So these two are connected. Similarly, one should have idea about what are similar triangles and what are congruent triangles. So, in similar triangles, two triangles can be called similar if they have same shape but different sizes and orientations. For example, you could have two such triangles. They have actually similar shapes, but their orientations are different and the sizes could be different as well. That is, for example, the sides here could be A1, B1, C1 and A2, B2, C2, but the sides have to have some proportionality. That is, A1 by A2 is equal to B1 by B2 is equal to C1 by C2. And their angles are connected. That is, the corresponding angles have to be the same. That is, theta 1 theta 2, theta 3, theta 1 prime, theta 2 prime, theta 3 prime. Then theta 1 is equal to theta 1 prime, theta 2 is equal to theta 2 prime, and theta 3 is equal to theta 3 prime. If these relationships are obeyed, then such triangles, two such triangles can be called as similar triangles. On the other hand, for congruent triangles, they are nothing but similar triangles but with same size. So everything else is same for congruent triangles. Additionally, size also is same. Then we can call those two triangles as congruent triangles. So these ideas in geometry will be useful, for example, when we do ray optics in physics. Our next topic is trigonometry. It is worthwhile to recollect some of the basic concepts of trigonometry. For example, in a right triangle, if you define the angle theta here, and if this is 90 degrees, then this side is called as the opposite side. This is the adjacent side, and this is the hypotenuse. And your hypotenuse side obeys the Pythagoras theorem, and you can get it as square root of opposite side squared plus the adjacent side squared. They obey this relationship. Then you can define angles sine theta. For example, sine of this angle theta is given by opposite side over hypotenuse. Cos angle is defined as adjacent side over hypotenuse, and tan theta is a sine over cos, so sine theta over cos theta, and hence this is equal to opposite side over adjacent side. And basically these are all ratios of these sides, and then you can get the sines and cosines of the angles. Also, there are some other relationships that one should remember. For example, sine square theta plus cos square theta is equal to 1. Sine 2 theta is equal to 2 sine theta cos theta. Cos 2 theta is equal to 2 cos squared theta minus 1, which is the same as 1 minus 2 sine squared theta. Similarly, cos theta 1 plus theta 2 is equal to cos theta 1 cos theta 2 minus sine theta 1 sine theta 2. If there is a minus sign here, that is cos theta 1 minus theta 2, then you would have a plus sign here. Cos theta 1 cos theta 2 plus sine theta 1 sine theta 2. Similarly, sine theta 1 plus or minus theta 2 is equal to sine theta 1 cos theta 2 plus minus sine theta 2 cos theta 1. Two other important laws in trigonometry are the law of sines and the law of cosines. So these laws of sines and cosines. So you have a triangle having sides A, B and C, and let the angles be defined as alpha, beta and gamma. Then the law of sines is nothing but the ratio of sine of the angle to the opposite side is equal to sine of the second angle to its opposite side is equal to sine of the third angle to its opposite side. This is called as the law of sines. The law of cosines helps us to calculate if two sides and one angle are known in a triangle. That is, if the third side, for example, C is not known, but we know the two sides A and B and the common angle gamma between the two sides, then the formula is for the third side, square of the third side C squared is equal to square of the first side plus square of the second side minus 2 times the product of the two sides and cos of the angle between them. This is called the law of cosines. So this helps us to calculate the third side if two sides and one angle are known. Dear students, I hope you learned something as well as you recollected some of the other things through this video, which is on basic math review for the physics for your higher secondary course pertaining to the CBSE NCERT syllabus. Please continue watching the channel for more updates and more videos on your higher secondary physics course. Thank you.